and then stop it. All right, awesome. The test for independence. When you stop that word, independence, okay, good job. Probability, if the probability of A given B equals the probability of A, they are independent. So if B happens and A doesn't care, they're independent, right? So if somebody in Missouri dropped their ice cream cone, will that affect my drive home?
No.
No, unless you're, the whole butterfly thing, all that kind of crap. Ice cream cone cause a monsoon. No, stop that. You guys, that's obviously a very silly example, but those are so desperately independent, right? I don't care what that, I don't even know if somebody just now did that. That's kind of weird. So this mathematically, it's exactly what I just said. So he drops his ice cream cone. The probability that I get home safely is the same as it was before. Right? They didn't affect each other. Okay, cool. So that's why this math makes sense. That's why this is what you check. You can't discuss it in a little paragraph. You have to. You could do this work and then discuss it in a paragraph, but you have to do this. You have to show me the math. Okay, so a silly example of independence is club and king. So what's the probability it's a king if I tell you that I got a club? So what goes on the bottom? 13 clubs, right? And out of those, how many are kings? One. Now how does that compare to the probability of a king just by itself? 4 out of, which is? There. So me telling you it's a club does not affect the probability that it's a king, because the ratio stayed the same. So most things in real life are basically dependent, right? So it's actually really difficult to get something beyond this kind of setup to get something that's truly independent. But we do have a little bit of a tolerance built in. It doesn't have to be exactly the same. Right? We talked a little bit about that before, but we can't start doing that until chapter 7, roughly. Talking about what that tolerance level is. Okay. Is that cool? No?
So would that be dependent or independent?
Since club happened and king did not care, what does it tell you, even just from a psychological standpoint? Just king didn't give a shit. Club happened, king is like, whatever, I'm the same. Are they dependent or independent?
Independent.
Yeah, exactly. He didn't care what that guy does. You can do it, you can happen or not happen. I don't care. I'll stay the same.
Okay, how do you write the formula for dependent?
Well, so if this is true, they're independent. If this is not true, there you go. Cool. All right, how are we doing? And the funny thing is you only have to check it one way, but it automatically works the other way. What's the probability that it's a club? A card would be a club that I pick. Good. 13 clubs out of 52 cards reduces down to 1/4, right? It's a lot like that. So what's probably it's a club given it's a king. So what's on the bottom now? What do I know about the card? I know it's a king. So what's on the bottom? 4. There's only 4 possibilities. Out of those 4, how many are clubs? 1. Yay, so they're still independent. It doesn't matter which way. If they're independent, they are independent, period. Whoever it happens, the other one doesn't care. Whichever way you do it, the probability is going to come out the same. Same thing for dependent. If it's dependent, no matter which way you do it, the probability is going to come out different. Because they affect each other. Okay, cool. All right. This semester, I seem to be angering some of you. Some of you look at me like, I want to hurt you. Okay? Sorry. It's probably a bad idea. Don't do it. Don't hurt me. Some of you probably could. All right. Anything else from homework or general concept of stuff. Our quiz is, I gave you a good decent amount of time till that double quiz. It's a week from today, if I remember right, October 1st. So you have even Monday to ask more questions until we actually do the double quiz. Downside of that is we're about to get into new stuff, so you don't want to let the old stuff leak out. Okay, y'all freaking me out. Let's get into, I don't want to look at you guys anymore, because seriously, some of you are looking like, stop with it. All right. So, what I want to do is, I want to show you why the stuff in chapter 5 works. So you don't have to do what I'm about to do, ever. It's just showing you why it works.
I have one last question about this. This is just about given, right?
Okay.
It's not. It has nothing to do with and or.
So an alternate. All right. So an alternate test would be if the probability of A and B equals the probability of A times the probability of B. Then they're independent. Because what is the formula for this in general? In general, the formula for this is probability of A times probability of B given A. So if this is true, what is that really saying? That this is that, which is the real test. So, I mean, some people do this, it's fine. And actually, it's this, you can interpret it the same way. If the probability of A and B is equal to the probability of A times the probability of B, then they're independent. What I love is when people calculate this by doing this incorrectly, and then they say, oh, it is independent because it's equal to that. And I'm like, of course it's equal to that. That's where you got it from. So be careful. Calculate and correctly if you want to do it this way. I don't know. Does the book say this somewhere? I'm always curious where this comes from. Because the real test really is here. This is like a level up from that. Since this is in here, if these are the same, then obviously this would be true. But, this is the real, just get to the point test. If that is that, they're independent. Yes, sir?
Also, you're going to give us the formulas for the quiz that we should put on the sheet?
Yeah. We'll talk about that on Monday. Yeah, so we'll put our formula sheet together on Monday. I just wanted to let us out early today, so. Because believe it or not, I'm not feeling that great. I know it's not coming across that way, but what's going on? Adrenaline. Straighten my wall out. All right, so here's the idea with section 5. I'm pretty sure we talked about this idea before. So I want to attack this in two different ways. One way we've already discussed. I just want to remind you guys. And there was a homework problem like this too. If there was just a midterm homework and a final in a class, and let's say the midterm counted 30%, the homework counted 10%, so the final would count 60%. Oh yeah. Of course, one class I took, there was only a oral final exam, and that was the only grade. They put us each in our own little room, and the teacher came around and gave us a question, and they came back later and said, show me your answer. Explain it to me. Like, oh, somebody had a nervous breakdown in the room next to me. She was crying, and I was like, I can't concentrate. So you guys remember this? We talked about this before. There's a problem in your homework that was sort of like this. If I made on the midterm, I had a great day. I made a 91. Homework, got a 93. And the final was not a good day for me. I got a 72. How do you get your average? Yeah, multiply the weights, right? I can't just add these 3 and divide by 3. Because the most heaviest weighted thing is the final, unfortunately, for this person. Right, for our fake person here. So to get the average, I would do 60% of 72 plus 10% of 93 plus 30% of 91. And that'll give me something. 72, 77, 79, 80, somewhere around there. What is it? Don't trust my brain right now. Don't trust my brain right now. What are you guys getting? It should be at least it definitely can't be lower than any of these.
79.
Hey, see, 80, all right, yeah. Wasn't too bad.
Yeah, 79.8.
Okay. And then, that's when they would come and say, come on, man, give me a B minus. Come on. No. All right. So let's investigate this a little deeper. I mean, this is one very specific situation, but they always act like this, and I want to show you why it does. So everybody got that there? Okay. So if I had to calculate the mean for a set of data, and the data looked like this. 4, 7, 8, 9, 10, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I want to make the example nice and easy because the results apply no matter what. So if I had to calculate the mean, how would you calculate the mean? Add them all up. So a smart way to maybe add them all up would be to say there's 4 ones, right? Plus 3 twos, plus 1 3, plus 2 4s. Is that cool? Divided by 10, right? Let me stop right there. You guys with me? Nothing major there. Just adding them up. Just doing it 4 ones plus 3 twos. So a little off the side work here. If you did that, what do you get? You get 4, 10,
2.1.
2.1. All right, so that's interesting on its own. So that would be 2.1. Now let me do stupid things with this that you would never do with this that will explain why what we're about to do works. Right? So isn't this equal to 4 tenths times 1 plus 3 tenths times 2 plus 1 tenth times 3 plus 2 tenths times 4?
Yeah.
Right? Okay? And isn't this 0.4 times 1 plus 0.3 times 2 plus 0.1 times 3 plus 0.2 times 4? So these are like weights. What percentage of the data is 1? 40%, right? 40% of my data was ones, so forth. Just like the early example, 60% of my average would be my final exam grade. You see the connection? So really, every time we learn a new way of somebody giving us data, we're going to learn new formulas for calculating the mean, calculating the standard deviation, but they really all go back to the basics. I still calculate the mean the same way. So this would still, of course, please, your God, let's see, 0.4 plus 0.6 plus 0.3 plus 0.8, right? And that is 2.1. Good. Thank God. So the way this data would have been given to me instead would have looked like this. Which got you? 1, 2, 3, 4. What were you there? So this is what's called a probability distribution. It feels a lot like our frequency distribution. In fact, these are really just relative frequencies in a way, right? This is like somebody made these into percentages. 4 of them are 1s out of 10, so 40%, that's relative frequencies. Let me stop right there. So probabilities in one sense can be looked at as relative frequency. So this is really either the probability of me randomly picking a 1 out of this would be 40%, or the percentage of things here that I see that are 1s is 40%, right? They both mean the same thing. But now the beautiful thing is, if they give me the data like this, all I have to do now is, how do I calculate the mean? What exactly did we do? Where did this number come from?
From multiplying.
Yeah, the x times the p of x, right? So I would want to make a column that was x p of x. And then, of course, how did I get 2.1? Added them all up. Okay, so now we know formula for the mean is I add up, what's that symbol? Sigma. Big old sigma. Add up all of the xp of x's. There you go. That's the formula for the mean when the data is given to me like that. Okay, so on one level, you just forget all this stuff if you want to. You just realize you just multiply across that and down. Right? That's really what's going on, but that's why it works. Now, some of you guys might argue, why don't I just get that and put 4 1s, 3 2s, 1 3, and 2 4s and just do everything the way I used to? Or maybe nobody thought that, but now you're like, yeah. What the hell, man? Well, because are you going to get tables that are that simple? If you did, certainly I'd love it if somebody did exactly what I just said. But you're going to get tables like this. Let's do another example. What do I got here? What have I got to be careful about? Yeah. So let's see, where am I at? 35, 52, 83, 89. Okay, good. Yay, I think that's right. So one thing to check. How do I know that this is a valid probability distribution? There are two things, actually. One of them is what we just did. One thing to check is that
equals 100.
Yeah, if you add up the probabilities. So if you add up the probabilities, it equals 1. Check. If it didn't equal 1, or at least close to 1, so if you get 0.999, that's okay, because it probably was rounded, just like when we made relative frequencies, right? But if it comes out to 0.96, you're missing 4% somewhere. That's too much to be missing. And a second thing to check seems really silly, but if you don't say it, you will lose points. Second thing to check is, are all the probabilities between 0 and 1? Because, of course, they can't be below 0 or above 1. And yes, they are. They're all between 0 and 1. Check. So it is a valid probability distribution. Okay, cool. Now, coming back to what I just said earlier. I could just make 4 1s, 3 2s, 1 3, 2 4s, get that list back and do it all. What would this require? 11 zeros, 24 1s. I'm already like, no, I don't want to. No, I don't want to do that. So this is what I want you to realize. The formula I wrote down, what's really funny is, what was the formula before for the mean? When I just gave you a list of data. What was the formula? No, don't. Standard deviation, not standard deviation. Just mean. Just the mean. How do you get the mean? Add them all up. Divide by how many there are, right? So does that look like this? Yes, it does. What's on the bottom of the probability? The number, n. On the bottom of this guy is n. So they really, really are the same formula. And I showed you just a minute ago how this really is coming from exactly what we did before. It's just a reorganization of it, because there's a quicker way to do it if they give it to me like this. So on one level, I love it if some of you guys understand what I'm trying to tell you. This looks like a brand new formula, but it isn't. It's just a reorganization of formulas we did before. It's easier to do if they give me data like this, xp of x. On the other level is realize if you have this sitting on your formula sheet, when do you use this? When you see x and p of x, probably. Would be a good guess, right? Okay. So, figure out what the mean is. Take a second. Figure out what the mean is. right, so what are we getting there? What goes here?
0.
0, because x times p of x, 0 times 0.11 is 0. 1 times 0.24 is 0.24. 24. 55. And if you add these up, that will be the... It's true. That'll be the sum. It'll be the mean, because that's the formula for the mean, right? The mean is whatever the sum of the xp of x is.
I think it's 230.
Is the mean. So if you add these up, what do you get? 5a. Somebody going to help me not make me do all this? 5a. 2.3. Now, if you just average these directly, what do you get? What's right in the middle? 2.5, right? Why is that a little bit lower? What do you think? The heaviest way to do it is 3, but what's the second heaviest way to do it? 1. So that kind of pulls it just a little bit in this direction. Do you guys see what I'm saying? If I would have made this guy 0.3 and that 0.11, it would have been even lower. It would have been pulled more in that direction. You guys with me? And that's why everybody hates the final, because it's the most heaviest weighted. Whatever you make of it is going to pull your average in that direction, right? So some of you hope you make it really good, and hope you make, or you just hope you don't make it really bad, because it's going to pull it in its direction. You kind of with me? Not as much as you think, though, actually, but we'll talk about that later. Okay.
Now let me ask you, does it always have to start at 0? Because like that one you didn't, and that one you
It doesn't. No.
Okay.
So this could be. I was going to say this situation could be. I go around and ask people, how many TVs do you have in your house? We don't have any TVs. I'm like, okay, I'm not that good. We got 1, we got 2, we got 3, we got 4, we got 5, right? So forth. So maybe that's what I asked these people, and 11% of them said they had no TV. 24% of them said they had 1 TV. You with me? That could be one situation that would lead to this kind of data set. Where's your data in this set, by the way? Where's your data?
P of x? Nope. X P of x?
These 2 columns are your data. This by itself is not good enough, because then it looks like you only talked to 6 people, right? And this by itself is not good enough, because then 11% of what? So together they tell you what your actual data set is. Are you with me? I'm going to come back to that in a minute when I show you a shortcut in this dude. Okay. And can you start to see what I'm up to, why I got that guy up there? This would be L1. This would be L2. What would he be? That's true. Gosh, this is the theme of the day. I love it.
Is it the summation of
L3 would be defined to be what?
The summation of L1 and L2?
No. I would sum it later. L1 times L2, yeah. Right? L1 is my x's, L2 is my p of x's. So to get L3, I do L1 times L2. Once I have those, I would go add them up. Right? Summation symbols should never show up here, because that's what you do. Once you have them, you add them up. You can't put a sum up here. Doesn't make any sense. Okay, good. All right, so what do you think I have to do next, considering where we come from? Like in chapter 3, we learned something very important about where we are in a data set is to calculate a z-score. And what does a z-score require? It requires a mean? It requires a standard. So we've got to figure out how, when it's presented to me like this, how do I get the standard deviation? Those are the 2 most important numbers to tell somebody about a data set. There are other numbers you can give somebody that tells more and more stuff, but if you could only give somebody 2 numbers about a data set, those are the 2 you tell them. What's the center, and how far away from the center do the things get? Bam, that's the quickest summary you can give somebody. So, I'm going to sort of cut to the chase here a little bit. Are you still good there? Oh, you didn't see any of that. Great. Okay. Let's see. Maybe we can do it here. All right. Well, let me do it over here. I want to put the real thing here. Let me show you where the real thing comes from. So what did we do before to get the standard deviation? We did x minus x bar and x minus x bar squared. Then we added them all up, right? So if I can't just add up the x's and divide by n, I had to do x times p of x. When I go to do my standard deviation, I can't just add these up. I actually have to take all of those times p of x. So let's do one row here real quick. And thankfully, I'm going to make this much simpler in just a second. So even if you don't want to write this down, it might not be a bad idea. This is where what we're about to do comes from. For this first row here, no, let's do the second one, because 0 is not much going on there. So 0.24. What is, oops, where did I get that from? Yeah, good. X minus the mean. What was the mean? 2.3. So what's 1 minus 2.3? Negative 1.3. And then what's that squared? I don't know if you guys know what 13 squared is.
169.
Yeah, so 1.69. And then I want to multiply that by the weight, because how often does that 1.69 happen? 24% of the time, right? So you have to always, whatever you're trying to work with, must be multiplied by the weight. Because how many of your data points are 1? 24% of them are 1, right? 24% of the people had 1 TV. So for each one of those, you're going to get this as the deviation. So you have to multiply this by 0.24. And what would you get there? Just a
1456.
456. Okay, 456. So you have to do that each time. Now that's
4056.
4056. Okay. So that's what I would have to do now. Let's make this a better formula right off the bat, because that's kind of disgusting. Right? Hopefully you guys are okay with me doing a slightly better formula. I need some room though. Oh yeah, I could just use it. Good. All right. So better formula. Okay. Not better handwriting. Fortunately. I'm not going to show you all the steps because this is not summation symbol class. You could actually take a class in that for years. Let's not do that. Let me just show you the first couple steps. Because I want to take this. Because what would you do after you get all this? You would add them all up, right? So I want to see the sum. And just to remind you again, what was the formula for the standard deviation before? Yeah, sigma squared would be sum of x minus the mean squared divided by
N minus 1.
n. And this is for a population, right?
Oh,
yeah.
We'll get into why I've got to call this. Well, I've got to call this a population. I might as well say it now. Because what's on the bottom of the probability? What's on the bottom of the probability?
Population.
1.
N. Right? You guys kind of with me? The bottom of the probabilities would all have n on them, right? Okay. So when I go to do this, this has an n under it, not an n minus 1. So it's kind of assumed that we must be talking about a population here. So that's why I use those symbols. It's kind of built in that it's over n already. So this is what I have to do every time. All right. So you can see, especially with what I just said, that the probability has an n on the bottom. That's basically the same formula as before. It's just built to handle it if they give it to me like this. Are we all kind of there right now? I mean, that's the same formula we used before because it's still over n, just like it used to be. Okay, good.
Is it ever n minus 1? Is it ever like for example, and it changes?
You could modify it. You'd have to multiply it by n over n minus 1. We're not going to go there.
Okay.
Yeah, so there's a lot of modifications you could do. That's for statistics too, if you ever take that. So I want to make this a little bit better. I'm not going to go through all the steps, but if you saw this in algebra class, what do you think you would do with that? No. Let's try it. If I saw x plus 7 squared.
Add and then square. Square root?
Yes, FOIL it. Cool. If I just, well, I'm not going to make you do it. Maybe I will now. But no, I'm not. But you should remember FOIL. How do I FOIL this out? I love that. If you love your FOIL, you probably wouldn't want to take me for algebra because I hate FOIL. FOIL is stupid. And I'll tell you why. The minute I put one more term in here, FOIL goes to hell. It would have to be something longer because you got more shit. So all you do when you have more than one thing to distribute, you just distribute them one at a time. If I had 3 things, I just distribute each of those one at a time. The idea is simpler than the mnemonic FOIL. But I'm not going to mess with your FOIL if you love it. Right? So you get x squared minus 2 mu x, right? 1 mu x and then another little mu. 2 mu x, so 2x. Plus mu squared times p of x. And let me just show you one more step. What would you get if you distributed this p of x in? Sum of x squared p of x, right? Minus other crap. You with me? All right. And recalling that the mean is the sum of x p of x. I mean, you can do a lot more simplifications. There's a lot more steps here. So here's what ends up happening. Instead of using the formula for the variance, instead of using this, we're going to use the formula because believe it or not, you guys see where that came from, right? You guys see where that came from? P of x times x squared. There it is, right there. That's the one thing I wanted to point out to you. The funny thing is that all the other stuff you get, simplifies to that. I'm not going to show you all that. Hopefully you're okay with that. Yes. Good. I'm glad to hear that. So that's the formula I'm going to use. Now, I know right now most of you are like either, what the hell's going on, or how is that any frickin' better? But I want you to realize, what do I already have to calculate anyway to get the mean? X times p of x. What's the only other thing? So I'm going to have the mean. I have the mean done. What does he need to finish it out? He needs a list of x squared p of x. So there's 2 ways you can get that. The way I do it is, if I just multiply by one more x, won't I have x squared p of x? Mm-hmm. The mistake people make all the time is they'll square this. If you square this, what do you get? If you square this, what do you get? X squared p squared. I don't want x squared p squared. That's silly. You're all like, that's not sillier than anything you're saying. So, okay. So we know this makes sense. I really desperately want you guys, that by itself, I can see the heart of a standard deviation is how far each data point is from the mean. You with me? So that makes sense that it is a standard deviation for something in this form. Do some algebra to it, which we didn't do all the steps because we're not into, there's a lot of weird summation algebra shit you got to do. But I see the first term, and the rest of it magically becomes that. That one you're going to have to take on my word, or you could try and do it and see how it comes out. I'm not going to do it. So what that means is, all I need is one more column. That's all I need. Just one more column instead of several more columns. I see one more column. I just need to multiply L3 by one more L1. Do you guys see how that would work? What is x times x p of x? X squared p of x. So let's see how this would look in the calculator real quick before we go any further here. If you want to borrow a calculator, there's several. Or if you just want to watch. Or if you have your own calculator, that kicks ass.
Oh, wait. Isn't standard deviation square rooted though?
Yeah, so that's the variance formula. I was just writing it quickly without. I don't want to use. We'll do the square root at the end. Go on. So it's real quick. Let's put this data in here and see how this works. So 0, 1, 2, 3, 4, 5, and then 0.11, 0.24. Where'd it go? 0.17. 0.6 and 0.11. So let's just verify what we got. Would you say that's roughly normal?
Yeah.
Yeah, very roughly normal. It goes up and then down. It's very roughly kind of normal. I don't know, just throw that out there. L3, how do I define L3?
L1.
L1 times L2. So go up, you highlight L3, and you say let that be L1
I thought it was L. Oh.
times L2. And let's see if we get the same numbers. Yay. All right, good.
How do you do it?
Hmm?
How do you do it?
All right, leave it. So highlight L3. You want to define that whole list. And you'll say it's L1 times L2. Because what's L1 got in it? X's. What's L2 got in it? P of X's. So if you want X times P of X, I'll just multiply those two lists together. And by the way, I've got a handout that actually has that whole kind of thing on there too, right? So now what do I want L4 to be? Yeah, because I need one more X for him, and it'll become the X squared P of X that dude wants. Right? Oh, shit. Feel free to remind me if I shift where I am. Let's see. So I want L4 to be another X times L3 where it's X P of X. And now I got X squared P of X. So those are my X squared P of X's. So who remembers, how can I add that list up real quick? Let's go beyond some crap. Let's go to one bar stats.
Yeah, I was going to say one bar stats
Yeah.
is your best friend in this one.
If I hit second quit, I get out of here. Is everybody with me on the L4 that's playing along?
Yeah.
So if I get out of here, I can go to stat, calc,
One bar.
one bar stats, and I want it to sum up the last list, right? List 4?
Yeah.
So I tell it list 4. It's going to give me a lot of crap, and the only thing I'm interested in is the sum, right? So don't worry about all this other stuff. The sum is 7.42. So how do I calculate the variance?
Mean squared.
Yeah, so we got all that there. Blah, 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 blah. So the variance is the sum of x squared p of x minus the mean squared. What was the sum of the x squared p of x? 7.42. What was the mean? 2.3. And the biggest mistake I see is people forget to square that poor little dude. So square that poor little dude. All right. So I'm just plugging and chugging into the formula now, right? I got the list I wanted, x squared p of x. I got the sum of that list. I can throw the whole thing, that goes right here. That's the sum, that's one number, 7.42. So somebody help me out. What do you get there?
Subtract 2.3.
So 7.42 minus 2.3 squared. 2.13, yeah. And then how do you get the standard deviation? Square root. Square root of that. 1.459. Okay. Say to yourself, I just saw this for the first time today. I will give myself time. I always love it when I see people and they're like, I don't understand this. I'm like, you just saw it for the first time. Give yourself a break. So, that's my standard deviations, and I know my mean. I know my standard deviation. Let's go one step further. Are any of my data points that are here, any of these data points unusual? So in your homework, you should have hit this idea. How far out do you have to go until you hit unusual?
3 standard deviations. Two standard?
2 standard deviations.
I thought 2 was within normal, though.
If you go out 2 standard deviations, you've caught everything that's normal. So anything outside of there will be unusual.
What is the 2 standard deviations? Is that the 99.7? And
No, it's 95.
95? Oh,
Yeah.
so 99.7 is the weird stuff.
No,
That's
gotta be
2.
careful. So, probability-wise, we say if something has a 5% chance or less of occurring, we call that unusual. So if I look at a normal curve, where would the unusualness start? 5% out here. So it must start at what would be 95% inside. That would be 2 steps out. Cool? So how do I go 2 steps out from the mean?
1.4.
Yeah, the mean was 2.3. So if I go 2 steps up, I add 2 of these. So it's 2.3 plus 2.9 roughly.
Yeah.
So I go up to 5.2 roughly. If I go down 2 steps, 2.3 minus 2.9, negative 0.6 roughly. Is anything unusual? No. Good. Everything's within 2 steps. So officially nothing there would be unusual. Somebody said they had 5 TVs, I wouldn't freak out on it. If you said you had 11 TVs, probably go, how big is your house? You know, there's an old commercial that had the guy watching the soccer match, and there was a TV in the drawer, and the TV in the bathroom, and the TV everywhere. Okay. So let me give you this handout. Let's see if I got everything on there. Okay, good. So just like an earlier handout, on one side I've got a worked out example, on the other side I got what I want you guys to do. Jump off of there. Straight, get an extra one. No, just 4. Don't worry, it's coming. I had to give them an extra one. Oh, yeah, sure. If you need a calculator, they're here. So, go ahead and try to do, use this as a guide, the one that's worked out, to try to do the problem on the back. Then when you're done with number 2, we'll look at it and then I'll show you the shortcut